Okay, so this is the LLM Tracer, a lightweight diagnostic tool that is built to hook into llama.cpp, and it shows you in real time what's happening inside a transformer model as it generates text. So let's first run this. Yeah, so this is our TUI. This is model topology. So every layer which our model uses is here, and the live tensor stream. So every single operation that the model performs, as you can see, is logged here. And this is the generation output. This is the layer inspector tab. So if I select some layer, it will show me its full details, the type, the shape, the D type, and all. And this is the runtime metrics and anomaly ledger. So whenever like it automatically flags the numerically suspicious tensors, like the outliers, so slow operations, high sparsity, and etc. So let's walk through the code and see. So yeah, our entire project rests on this one feature, cb val, which is this llama.cpp already exposes uh, a callback field. So like when you set this, llama.cpp calls your function before and after every single ggml operation, and during inference, so like every matrix multiplier, softmax, layer norm, etc. So we never touch this, that touch the source code. This is what non-invasive means in our problem statement. Now let's look at the callback signature function. So this runs twice per operation. So like when ask is true, it's llama.cpp asking us like, do you want to inspect this tensor? And we say yes by returning true. And when it is false, then the operation is already finished. So we calculate just the how long it took. And so every tensor has a name. The like q and the model which are using has tensor named with a number baked in, like q cur 12, k v cur 0, like this all. So uh, we found these names by literally logging every unique tensor we saw to debug file, and then pattern match them. So and the every we like when we capture a tensor, we run three checks. The first is the sparsity, maximum activation, and the latency. So the sparsity tells us like what fraction of values in the tensor are exactly zero. So if it is more than 85%, then it's a sign of dead neurons. Or the max, when max activation is above 6, so which is it causes overflow. So and when if anything took over 100 milliseconds, it gets flagged as bottleneck. Okay, so like every a single inference run, even just generating 120 tokens, it produces lots of tensor events. So if we store all of them, our memory would balloon. So instead we use a ring buffer capped at 150 events. So but this created a bug that we had to fix, like when we had tensor like embedding layer, so it fires once per decode call. So with 150 other tensors flowing through in between, that one entry would get evicted before you ever select it in the UI. So the fix was this structure. This map is never evicted, so every push also updates this map, and no matter how stale a layer's event become in ring buffer, the layer inspector can always show its last known state. Yeah, so this apps run three threads. The first one is the engine thread that actually runs the model, so loading it, tokenizing the prompt, calling llama decode, and like all this happens in there. And then we have refresh thread, so it wakes the UI every 50 milliseconds, and so it keeps redrawing even when no tensor had just arrived. So, and then we have the main thread that runs the F2X UI loop. So every callback fires on engine thread, but UI reads the on the main thread. And so every inference has two phases. The first one is the prefill, so it processes whole prompt at once, and then we have generation that takes one token at a time. So every single call to Llama decode is every single call to Llama decode, whether prefill or generate. So it all are callbacks. It triggers a callback hundred of times. So funds for every tensor operation in all 24 transformation layers. Now let's see our UI render. So the F2X UI rebuilds our entire UI as a tree of elements every frame. So each panel, which you can see, is a lambda that locks the relevant mutex, reads the data, and then returns the F2X UI. And like this is all the TUI part. And then we have the catch event. So like all the keyboard handling goes through this catch event. So this is like how we implement the quit and pause and all.